Hello from a wet and windy Aberdeen. As it says on the slide, my name is Richard Arnold. I'm Senior Technical Consultant at Premier Oilfield with Corex, and I've been in the industry for over 40 years. And my experience has spanned managing and running analytical labs in the UK, and the Netherlands, and in South America. And I've been involved in core analysis and formation evaluation projects across the globe, principally in the North Sea, but obviously I spent some time in Latin America and also onshore Europe, but also projects in the Middle and Far East and Africa as well. So without further ado, let's get going. I'm hoping to give you just an overview, really, of what can be done with cuttings over and above the traditional analysis. So I'm just going to touch on what that has been in the past. Then we're going to talk about petrographic analysis, high resolution petrology, and particularly geochemistry, chemostratigraphy. The applications of some of this enhanced mineralogical data, and then have a look at how we might be able to fill in some of the petrophysical data gaps. And as it's a hot topic at the moment, carbon capture and storage and abandonment. These are areas which I believe that cuttings can give us information which is not readily or not used very often at the moment. And then we'll draw some conclusions. So I hope to be able to answer, we've had a lot of questions. I hope to be able to answer them as we go along, but please feel free to post your question again. We'll try and get, if I can't answer it, we can get one of our technical specialists to fill in the gaps. Okay. So basically, we're posing the question: what happens when you don't have traditional core material? You don't have sidewalls, particularly rotary sidewalls are becoming more and more popular. But all wells, but both of the acquisition of core and of wireline sidewalls is often considered an expensive operation. But all wells have cuttings and have had since we've been drilling over time. So just a quick recap on where the cuttings come from. For those of you who are not familiar, this is the schematic here. Let me just get the laser pointer up. There we go. This schematic here shows the business end of the drill string with the drill bit. We've got drilling fluid coming down the pipe annulus, and then the cutting edge here. The cuttings are then washed to the surface, and that's where we're able to collect them. And this schematic here shows the whole system with the drilling fluid passing down the pipe, then back up the outside, washing out the cuttings, which are then separated from the drilling fluid on the shale shaker. The fluid is returned to the mud pit, and the solids are discharged. And that's where we pick up the cuttings at the surface. So we can see here is a traditional mud logging operation. You can see the shale shaker in the background. Here are the cuttings coming out. This is quite a basic operation. I'm not quite sure where, but and this guy is looking at the cuttings, perhaps picking formation tops. This is the traditional roll of cuttings. The mud logger would be looking to pick out the formation tops, be doing a description, brief lithology, maybe some mineralogy. Then samples would be used for biostratigraphy and possibly fluid identification and organic content. So through a description, and then maybe some analytical work. And an example here of the old style hand-drawn mud log with a handwritten description of the sample with abbreviations. I'm sure a lot of us have used these abbreviations over the years. And I do recall when I first started in the industry, one of the major skills of the mudlogger was to be able to use a lettering system, and so that these could be easily read and transmitted over the fax machine, which is the way in which data was transferred in those days. For those of you who don't remember what fax machines, so you just have to look it up on Wikipedia. So and this is a question which came up about the issues of using cuttings. There are things which need to be addressed. Is the frequency of how often do I take cutting samples? This is obviously determined by during the well planning, and depends on how quickly you're drilling, how heterogeneous the formation is. Remembering that logging tools have a resolution maybe every of about a meter roughly. So if you've got beds which are thinner than that, you may want to consider taking cuttings at least at the meter stage. But that may be, if you're drilling at 60 meters an hour, that's going to be a lot of work for the mudloggers. And how representative are the samples? You've got to try and avoid smearing, so you need to be able to take the cuttings at the appropriate time when they reach the surface. So the lag needs to be carefully calculated, and that's one of the jobs of the mudlogger and the mud engineer. The cuttings themselves, there's a lot of material which is also transferred from the bottom of the well. Principally cave-ins, which are bits of the well bore which fall into the well after the drill bit has moved on. They need to be removed during the processing, as does lost circulation material, walnut shells, whatever's gone into the well, maybe mud additives, solids, etc. So they need to be picked out. The effect of the PDC bits is widely recognized, and it does limit some of the analysis which we can undertake due to the fact that they quite often disaggregate the sample, so you've got individual grains. It's impossible to measure a porosity when you don't have any pore space. So that's something that needs to be considered and taken into account in the program of analyzing the cuttings. The collection needs to be consistent. It's often the job of the junior mudlogger to collect the samples, and they need to be aware of how important and how in the middle of the night it's still important to make sure that you're collecting the cuttings correctly. And curation, what I mean by that is that care needs to be taken in looking after the samples. Often they're we've seen samples that have been in a warehouse somewhere. They're not very well labeled. They've dried out, so they make it more difficult to process and get realistic data from. So moving on. So as I said, once we've got the cuttings, and as you can see here, we've got some examples here. The samples need to be cleaned and dried, depending on the drilling fluid that's been used. If it's a oil-based mud or diesel or whatever, we need to remove that. And then the samples need to be dried, and they end up in this sort of form. And you can see here there's a collection of cuttings have been separated out. So we need to examine them under a stereoscopic microscope to remove, as I mentioned earlier, the cave-ins, the lost circulation material, drilling fluid, solids, etc. Anything which is not representative of the formation, and also to check on the validity of the samples. Is it what you're expecting to find? If you've got a sand shale sequence, are you seeing that in the cuttings, or are they, as we mentioned previously, smeared, so mixed up, in other words? So at the initial screening, we do high resolution microscopy. As I said, this is an image from a stereoscopic microscope. We define the lithological spectrum rather, and samples are then prepared for thin section analysis, and are often using SEM to look at the pore morphology to see if we've got pore space, which we can then make some measurements on later in the process. So here we've got some nice examples of SEMs with kaolinite. This looks like some pore bridging illite. So there's lots of information that we can extract from the petrology, and that is comes in the form of the description. So the thin sections are prepared in the traditional way, impregnated with a dye and staining to identify different minerals, the carbonates and the alkali feldspars. The dye allows us to spot the any porosity present, and this can be the value of that can be determined by modal analysis and point counting. So the description normally includes, regularly includes texture, mineralogy, porosity as I mentioned, the relative abundance of the different detrital and orthogenic components, and that is often confirmed by point counting. And just some examples of, sorry, I'm on a slight issue with my mouse. Just some nice examples of different thin section, showing the, here you can see, and this one here, you can see there's quite a lot of blue between the grains, which we would consider to be porosity. We've got different minerals identified in these examples. We've got some detrital clay down here, plagioclase, kaolinite. Up here we've got dolomite, and there we've got porosity in the these are the pore spaces. Again, SEM, an examination is undertaken on selected lithotypes from the cuttings, and we make our specialists make a detailed description, and they're looking particularly for information on the pore geometry. Are the samples that they're looking at, are they representative? One of the things I should have mentioned in thin section, one of the things that is important to identify from the thin sections particularly, but also from SEM, is whether the samples, the cuttings have been damaged in transport. Have they been fractured, both during the drilling process and during the transportation to the surface? It's important that we know this, so that we can eliminate samples which have got excess porosity, which has been induced by the drilling process. So we don't get optimistic porosity values. Some of the other analysis which is undertaken, particularly in the unconventional part of our industry, is the measurement of TOC, the total organic carbon, which is, as it states on the slides, a measure of the organic richness of the rock. So it could be used for source rock analysis, and in the unconventional market, the source rock is also often the reservoir material. So rock eval-pyrolysis, using these types of instruments, is used to identify the quality of the organic material present, what type it is, its thermal maturity, and then further analysis will give us an idea of the various hydrocarbon markers, S1, 2, 3, the residual carbon S4, and again the thermal maturity. So what has the rock gone through during its during any hydrocarbon evolution? And finally, and this applies, my feeling is that this applies mainly to fresh samples. It is possible to extract oils and condensate material from the pores. So there is pores that are present in the cuttings, and to do fluid fingerprint analysis. Obviously, you need to fingerprint the drilling fluids as well, and that gives us valuable information about the hydrocarbon present in the rock, in the reservoir, and maybe in the surrounding overburden and below the reservoir section. And it's also possible to get information on the gas present, if that is one of your requirements. This is not an area of my expertise, so if you have questions about TOC or gas analysis, gas and oil analysis, please feel free to ask, and we will put you in touch with the relevant specialists within our group. So moving on to one of the main things which we undertake for cuttings analysis these days, and that is the use of X-ray fluorescence analysis. This is a technique which has become popular in recent years with the advent of the instruments such as the one here, this Brooker 5i instrument, which is the one which we use. We use this particular instrument because we developed our own proprietary, this is Premier Oilfield Group have developed a proprietary calibration, so we don't use the one which comes with the instrument, one that we've developed ourselves. And this allows us to have a great amount of confidence about the quality of the data that we're able to produce. So we take the drill cuttings. In short, we take the drill cuttings. They are homogeneous once they've been cleaned and picked of cuttings and such. We pulverize the sample, and then they are then formed into sample pellets to ensure proper density distribution. Excuse me a second. So the X-ray fluorescence, it's a technique which excites the electrons in an element, and it measures the characteristic byproduct X-ray produced by from that excitement. Sorry, with X-rays. If you want to know more about the actual technique, we can provide you with quite a lot of information. We may have a presentation later in the year specifically on XRF chemostratigraphy. So as I said, we're looking at elemental data. So this is information which would be equivalent to using the elemental spectroscopy logging tools. So we get information on 12 major elements highlighted here in, I hope this is green on your screens, but sodium, potassium, magnesium, calcium, titanium, manganese, iron, and of course aluminium, silicon, phosphorus, sulfur, and chlorine. And then we've got 21 trace elements. I'm not going to go through all of those because some of the names I can't pronounce, but importantly we've got things like thorium, uranium, vanadium, chrome, and nickel, copper. And what we have identify the elements, normally attributed as oxides. And there's quite a well-known, well-established algorithms to allocate the elemental data into mineralogy. So all of the silica is allocated initially to quartz, and then to the to opals, etc., etc. The aluminium oxide is then that's applied to the total clays. The calcium oxide predominantly goes into it. In the first instance, is all allocated to calcite, and then into dolomite, etc., etc., using this sequence of allocation. So and what we do is we can model the mineralogy using the XRF data as shown here, and then that can be calibrated against X-ray diffraction data. X-ray diffraction data gives us mineralogy as opposed to elemental values. We can compare the two, and then, as you can see here, there's a reasonably good match in between the two. Again, other examples are available. So moving on from that, we also have the possibility of hierarchical cluster analysis, in which particular minerals are defined into chemofasces by their particular elemental affinities. So unsurprisingly, the calcium, magnesium, manganese, and strontium are associated with carbonates. These minerals, molybdenum, uranium, nickel, are normally associated with redox and organic rich minerals or formations. The detrital minerals are represented by, as you might expect, the major one being silica, but aluminium, titanium, potassium. And then moving down, sulfides, obviously sulfur, iron is strongly represented here, and some of the other trace elements, phosphate, obviously, salts, chlorine is here, but also sodium is a strong association, and then barite, obviously barium is very prominent there, but also sulfur. So once we have the elemental data set, this can then be, as the slide suggests, that this can be processed through a geostatistical technique called hierarchical clustering, which is used by our team led by Dr. Harry Rowe at the university, principally at the University of Austin in Texas. Harry is now our director of geological studies, and basically this, as the slide here shows, a reordering of the samples based on their chemical similarity, which are then can be then interpreted into chemofasces. And this heat map is showing distributions of different minerals. The warmer orange red color indicates a high concentration. So in this particular case, we've got LST1 and LST2 here, which have been separated out as different chemofasces, which have high similar concentrations of calcium. And it's in thin section and such, it may be, or if you were looking at core material, it would be quite difficult to differentiate between these two. But when we look at the next door at the nickel, we can see there's quite a difference in the two distributions, with the nickel suggesting that the LST2 was deposited in more anoxic conditions. Another example of a heat map, which is quite clearly these chemofacies here are associated with carbonates. We've got a lot of calcium carbonate. We've got magnesium carbonate. So dolomite, ferrone dolomite, and manganese dolomite also. Over here, this section is more detrital material. So we can differentiate the different facies and assign them a depositional environment. Then what we can do then is use the chemofacies to define the actual distribution of the chemofacies in through the stratigraphic column. Excuse me a second, my voice is getting a bit dry. So here in this case we have, and we can see cyclicity in the formation. We're moving from a sandstone, perhaps a beach sand or something like that, into deeper water perhaps, and then quieter conditions with dolomites and then limestones being formed, and finally we end up with an oxic sulfur-rich, perhaps deeper water, or a deep water marine environment, and then we see it coming back again, and then again later we have another cycle here. So maybe we've got a change in sea level. That type of thing can be used for the interpretation of the formation. So looking at the distribution of the elements, this is an example well from the Middle East, which we've got 11 major elements which are measured using the XRF, and these are plotted as percentages of oxide. So we can see some of the here with this is obviously interpreted as calcium rich as a limestone, and here where the limestone dips, the calcium dips, the aluminium increases, the silica increases, so we've got something more a more clastic formation there. We can generate an elemental gamma ray from the potassium, thorium, and uranium content. I should have pointed out, yeah, that peak is also seen in the potassium here, and then we've modeled the mineralogy, and we've got a facies change quite evident at down here at 7,900, where we change from the calcite rich, that drops off. We've got more aluminium oxide, we've got more silica oxide, so quartz, more titanium, a lot more potassium, and some sodium as well. And that mineralogy is interpreted as I say, being a sand here, and maybe this is total clay. Looking at the trace elements on the same section, we've got 18 different trace elements, and these are reported as parts per million, and these are useful for well-to-well plotted against the mineral model, and they're very useful in well-to-well correlations. They're a little bit more, perhaps a little bit more sensitive. Excuse me. So we've got the redox sensitive trace elements, so cobalt, nickel, copper, molybdenum, and uranium. So they're giving perhaps an indication of the paleo environment. So where they're higher, we've got more quieter conditions. While the gentle, while the diagenetic immobile trace elements, so yttrium, zirconium, and niobium, can be used to create chemostratigraphic zonations and correlations. We back that up with XRD analyses. We've got, we'd use, in this particular case, we did 10 XRD samples were analysed for whole rock and clay. And those were used to constrain the mineral model. The XRD, calcite and dolomite, these are plotted separately, and they show good correlation with the modelled mineralogy. Again, the quartz and feldspar and total clays, they exhibit similar behavior to the mineral model, validating the data. And in this particular case, the last sample that was analysed, when we looked at it in thin section, we found that there was pyrite, and the mineral analysis also, the modelling analysis also picked up the same information. So that, again, confirmation of the work. This is an example of a well from North America. So this is an unconventional play, but what we're seeing here, we've got elemental gamma ray. So we've got total gamma, synthetic total gamma, and a synthetic spectral gamma with the different elements, potassium, thorium, and uranium split out. As you can see, sorry, the label is over it there. You can see a change in the lithology there, which is reflected in the mineral model. It's also reflected it's also found in the gamma ray. And then when we look across, we can see changes in the actual mineralogy distribution. Using the modeled mineralogy, we, in conjunction with the wireline density, we can calculate total porosity. So that gives us a further handle on the porosity values found in the well. And in this particular case, as I said, this is an unconventional play. We've got total organic carbon indicated by the redox sensitive elements, uranium, nickel, lead, and etc. So we can plot that. I do apologize. I seem to be having some problems with my mouse. And finally, we have a brittleness index calculated from the mineralogy. So the ratio between the brittle and total components, which can be used for wellbore stability and in completion and fracking planning, exactly where the best place is to put the completions in, and those which are most likely to be avoided. If we look here, we can see this is blue, so the index is low. So this is a zone, although it's high in total organic carbon, it perhaps won't frack very well because of the ductile clay minerals, which you can see here are high. Further down, we've got an increase in brittleness, so this may frack more easily. It's easier to propagate the frack, and maybe the best zone to pick, although it may not be the highest one of organic content. So as a package altogether, the geological interpretation, what we can do is we can generate and define a fascist scheme, fascist top. That can be visualized into a log like the one we see here. And the sedimentologists can interpret that into the various architectures of the reservoir, or perhaps the overburden, and it gives an interpretation of what we can see on the seismic traces, filling in a lot of detail which you can't get from seismic, and is difficult often to get from wireline data. So just to emphasize that, we have enhanced well correlation, so we can trace a flooding surface from one well to another, and then integrate that. If we've got multiple wells, we can integrate that into a sedimentological or basin modeling situation. Now, looking at the some of the usages of the chemostratigraphy data, or data generated from chemostratigraphy, one of the interesting ones that we have is the utilization of the data to optimize completions. And in this particular example, I hope you will be able to see this. This is the well bore trajectory for a horizontal well in North America, and we've plotted out the quartz, clays. This particular example, we've got TOC and then brittleness. We'll have a closer look at those plots in a moment. But needless to say, this data was used to adjust the stage boundaries for the completions, rather than using the generally utilized geometric spacing model. That adjustment, which was carried out without having to use an expensive logging suite, allowed the work was done by our colleagues in Premier Oilfield Group in Houston. Did that at a much cheaper cost than running the sophisticated logging tools. So what was able to happen was the cluster and stage spacing was adjusted. The number of stages was reduced, with a net increase in production. And they estimated, they did a workshop on this with the SPE, and the reduction in number of stages and increased production saved on average about $600,000 per well. So you can see that it could be significant value in using the cuttings for this type of work. So looking at the individual plots, we've got two wells, a comparison of two wells here, two horizontals. The top one is showing this is quartz distribution. And well number one is showing quite a varied range from 25% up to over 60% of quartz, whereas well number two is much more uniform and a lower concentration of quartz. So we really keep that in mind. So looking at moving on through the different mineralogy, when we look at the calcite, again, well number one has a wide variety in quartz calcite distribution. Well number two, again, similar to the quartz, has a much more a lower uniform distribution of calcite. And finally, looking at clay mineralogy, well number two as you can see, is much more red and darker colors, whereas well number 1 is more in the green range. We wanted to and some grays. So well number 2 is up here above 24% clay, which explains some of the other mineralogy we've seen in the other plots. So what we're able to do is convert that into a brittleness index, where and this is demonstrating that well number 2 is more clay. Because it is more clay rich, we have a reduced brittleness index, which is to say that well number 1 is more mechanically brittle, so would frac more easily than well number 2. So propagation of the frac in well number 2 would not be propagated as far as the same amount of energy in well number 1, and obviously that has a big knock-on effect on the economics of the frac operation, which I think is quite a neat application. So moving away from chemostratigraphy and mineralogy specifically, we've talked about geological description, mineralogy. What other data options are available? And some of these are more guided towards special core analysis applications. So we can get porosity and grain density in lab measurements. We can cross-check those with the data from thin sections and SEMs, and some other techniques which we'll touch on briefly. We can perform, depending on the quality of the cuttings, we can perform high pressure mercury injection, which can give us capillary pressure data, but also quite interestingly, an example here of pore throat radius from cuttings, and we can see a bimodal distribution here, which gives insights into the permeability distribution of the sample. We can calculate a theoretical permeability from this sort of data. More recently, we are able to perform micro CT scanning and analysis, which leads us on then to the possibilities of digital rock physics. This can also, but this can be, in the first instance, can be used as a cross-check on the porosity, and then more traditional work of grain size analysis, laser particle analysis. And then finally, recently we've been doing some work on NMR, which I'll say a few words about. So with the micro CT scanning, we can scan the sample and then look at the interior in more detail. We can identify the porosity and the mineral distributions. And as I said, this leads us on to the possibilities of doing digital rock physics, which I'm not going to go into today, but you know, it's just it is a possibility. And here's an example of particle size analysis, different samples which were analyzed using a laser sizing instrument, which gives us information on on completions, what screen sizes need to be used, and that type of information. Moving on, because I am aware that time is moving by. We've been doing some work more recently on cuttings analysis, cuttings NMR. The biggest problem with NMR measurements on cuttings is the irregular surface area, because that gives us a high surface fluid content. But some techniques have been developed in conjunction with our colleagues at Green Imaging Technology, and I would refer you to this paper, Whitman et al. It was published last year from the UR Tech paper 3290. If you would like a copy of that paper, and there is also a quite a nice little presentation on YouTube by Brett Whitman, explaining what they did and how they married the NMR data to the chemostratigraphy mineralogy. If this is an area that you're particularly interested in, I suggest that you, if you get in touch with us, let us know and we can send you a copy and the link to the YouTube. But the issue, as I said, is the irregular surface with the cuttings, and that's overcome by using using a centrifuge. So the value of the NMR porosity we found is almost a function of the speed in which we spin the samples in the centrifuge. Oh, sorry, my mouse seems to be giving me trouble this morning. So what we have here is a plot of the volume, detectable volume, and the centrifuge speed. So basically, the faster we spin the sample, more fluid comes out. It's just the same as a washing machine, really, but a rather expensive washing machine. And the fluid held in the small pores are held there by capillary forces, and this is what we want to measure. So we've got a plot here of NMR from cuttings, and we've got a rather good T2 values are agreeing quite nicely. This is an area which we're continuing to do more work in, and we'll be happy to discuss with you if that's an area that you would be interested in. I would emphasize, though, one point, that it's important, as always, that you use more than one area. It's very important to identify whether there's microfractures present. So thin sections, SEM, and these days micro CT is basically a requirement before we get down to so that we get the validity of the NMR data. Some other tests which are used with cuttings is the capillary suction test, which basically, the higher the clay content, the greater the interaction between the formation material and fresh water, which is expressed in longer the capillary suction test time takes, and gives us an evaluation of the swelling potential of the formation when exposed to different treatments. The roller oven does a similar test in which sieved cutting samples are rolled in a treatment fluid for a period of 16 hours, and then they're re-sieved, and we see if there's any change in the distribution. Basically, has the sample disaggregated. So these are simple tests which can be run on different fluids, so you can see the effect of the different fluids on the rock fabric, used mainly in completion work. It's something you may not be cognizant of. So as time is pressing, I'll move on quickly to a quick word about carbon capture and abandonment. So what inputs are needed for this type of work? Speaking to an abandonment ops geologist recently, they work with flow units based on the drilling records. If they've got LWD and wireline logs, they use those, and they use the lithology logs from the mud logs. Obviously, in old wells, we're going back to the almost as back as far as the original hand-drawn wells. So the cuttings can provide, as I hope I've demonstrated, detailed mineralogy and sediment from that sedimentology. We can derive porosity and permeability, and particularly in the case of carbon capture, we can measure pore throat, pore size distributions, and from that we can calculate threshold pressures. So we can find, we can indicate whether the whether the seals in the reservoir are they going to hold over the long periods of time, which carbon dioxide needs to be stored. We're talking about hundreds, if not thousands, of years. So, you know, we need to get as much information to secure this, the carbon in the current climate. One of the other things we've been doing, the Premier Oilfield Group has done, is we set up we acquired a sample library in Midland, Texas, with over material from over 200,000 wells, cuttings, and some core. And what we've done with that, as you can see, is there's quite a lot of these, a lot of samples. We reorganized it and we began analyzing samples. And we generated, or we put these into a cloud-based platform, which allows you to access this data. It's by obtaining a license, which is free to obtain. You can find out what samples are available, and then it's possible in the US to purchase that data. I mention this because this is a model which we can propagate for internal use, and it's proved very popular in this format. If you'd like to know more about DataStack, there is you can go to pofg.com DataStack, or again, if you'd like to contact Jennifer or myself, we can give you some more information about that. Okay, so just to wind up, so why work with cuttings? I postulate that exploration risk can be reduced by using direct data from cuttings, rather than just using indirect seismic and wireline log signals. So a maxim that I always use is, if you can't touch it, it's not real. With core, you can touch. This is a way of touching the reservoir, the only opportunity you get. If you can't take core, you've always got cuttings. So cuttings can reveal properties of reservoirs and information on the top and lateral seals. It can give us access to sedimentology and petrographic analyses through XRF, XRD, SEM, and thin section. Cuttings are widely used already, but can be used for well correlation by identifying the mappable surfaces. And it can reveal, as the note says here, potential challenges in the overburden. Often logs have been run in the past in minimum in the overburden, and certainly core is very rarely taken in the overburden and the top parts of many reservoirs. So cuttings could help de-risk those parts of the reservoir, and can fill in the gaps between cored and uncored wells. And we can generate cuttings to core calibrations. So I hope I've demonstrated that we have a customizable integrated workflow. We can utilize XRF, XRD, thin sections, SEM, pyrolysis, and then NMR mercury injection. These can all be integrated in with the wireline logs and the LWD data, and can help to refine the petrophysical sedimentological models, which are then used for the reservoir modeling efforts. And what we can do, we bundle these together as a package. You need to do the geological description to validate and prepare the samples in pre-screening to be able to do the other analyses. But we're able to process the samples in quite quickly. I was asked, one of the questions I was asked is, can this analysis be carried out at the well site? Some of it can, XRF, XRD, and some petrology can be carried out at the well site, but we're able to process at Premier many hundreds of samples per day for XRF, and about 60, 70 XRD samples for calibration purposes. Some of the other tests, obviously, the capacity is a bit lower, but we can tailor that to your particular requirement. So with as we're nearly at 11 o'clock, I'm afraid I've rambled on for too long. I'll see if there are any questions.
So we did have a few questions through the Q&A during the session, Richard. We also have our list of questions we received prior. Do you want to handle these now? We are pretty bang on 11, so I don't know if you might want to get back via email or.
I'm just reading through the questions.
Is there anything specific you would like to highlight now, and then you can maybe get back later via email?
I think it's probably easier to as we're tight for time. I'll just promise that we'll get back to people with the questions that they've asked. Just reading down the list. One question was from Mohammed Abbas at Charion. Can we create synthetic logs from drill cuttings? I hope I've demonstrated yes, we can. Lithology, logs, gamma ray, porosity, mineralogy, etc., and also the brittleness index. I think as we are that tight for time, the best thing to do is for me to post some answers back to these various questions. But thank you for all the questions you've sent, and I do apologise for talking for too long. But some of the questions are quite technical, so you know, they're not just a single sentence. So we will get back to you on them. Okay. So thank you all for your attention. I hope I haven't sent too many people to sleep, and I'll hand you back to Jennifer.
Perfect. Thank you very much, Richard. And thank you again, everyone, for joining us. Yeah, as Richard said, any further questions, just feel free to get in touch, and we will also follow up with your previous questions received and questions during the session as well. So thanks very much for those. You will see a link tomorrow in your emails with today's recording as well, so keep a lookout for that one. Just doing a quick look forward, if Richard just moves to the next slide quickly.
Could I just add one? Can I ask a question to the audience that I would meant to ask them at the beginning to do a poll of do they use cuttings? My question to them is, will they consider using cuttings in the future? So if you can let us know
I can pull that up now if you want to do that quickly, Richard. I'll just launch the polling and then I will talk about what we have coming up. If you move on to the next slide, please.
Yeah. Okay.
So on the 18th of March, Justin Green, our well-known expert in our formation damage series, will be back looking at organic and inorganic scale for us. And then on the 15th of April, Jules Reed, another familiar face, will also be back presenting on gas liquid core tests, a solution challenge. So look out for details of these released in the coming weeks. All registration info and links will all be up on our Premier Corex, LinkedIn and social pages. If you give our page a quick follow as well, that means that you won't miss any of these sessions as they become available. And also just a quick note, if you have missed any of our previous webinars as well, then you can check these all out on our Premier Corex YouTube channel. So all of our sessions are uploaded there for you. As always, if you'd like to pass through any suggestions for upcoming schedules, topics of interest you would like us to explore, either at public sessions or through sessions specifically tailored by us for your company, please do get in touch. Really enjoying hosting these for you. And the main motivation really for doing this is to bring great content for you. So we want to make sure we're bringing you fresh and relevant topics really in your areas of interest going forward. I will just stop the poll there quickly, and yes, share results there. 94% say they would now consider using cuttings to generate data to use in well evaluations. So that's a fairly overwhelming response there. It's good.
Well, I'm glad that everybody obviously enjoyed it then. So.
Okay, thank you for running over there shortly. We always try to keep the sessions to the hour on the dot, but we always tend to run over just a few minutes extra. But that is all from me. Thank you to Richard and to everyone again for joining us, and hope you can join us for more sessions in the coming months. Thank you, everybody.